Educational Module. Machine Learning. Learning Unit. Core. Data Pre-Processing. Real-world data are noisy, unreliable, and filled with errors. Pre-processing is an important step that must be performed before the data are ready to be used in a learning algorithm. Missing values. Out-of-range values. Impossible data combinations. Typing errors. Inconsistencies. Basic steps are the following. Data cleansing. That aims at fixing missing values, outliers, and inconsistencies. Missing values can be replaced manually or automatically. Data transformation. Perform binning on data such as age, since the age of people is better represented in groups. Perform normalization. Perform aggregation. Feature engineering and selection that aims at dimensionality reduction. Noisy, missing, and inconsistent data are caused by a variety of reasons. They can be fixed manually or automatically with the help of clustering, outlier detection and regression. A way to do that could be by utilizing the average of existing values, but one should make sure the average is of all instances to avoid bias. There exist two versions of binning: distance-based, where the total range of values is split on parts of equal length, e.g. splitting age at 15-year intervals; frequency-based, where the values are split in a way that guarantees the same number of instances on every bin. Binning is a subset of discretization. Discretization to reduce the size of data can also be performed in other ways, e.g. entropy. There are many ways to perform normalization of the data: min-max normalization, z-score normalization, etc. Before going into feature selection, we must first explore the concept of features in machine learning. In machine learning, a feature is an individual measurable property or characteristic of a phenomenon being observed. Features are the most important ingredient of machine learning. Feature engineering is the process of using domain and general knowledge to create features that will assist a machine learning algorithm. It is a mostly manual process and is the most important art in machine learning. The need for manual feature engineering can be obviated by automated feature learning. Example 1. New information is derived by the fact that certain days are holidays. Example 2. Machine learning challenge for an image recognition task. The modification and creation times of each image file can be used as an additional feature. Images of the same type were created at similar dates. Feature selection is the process of selecting a subset of the original feature set, that includes the most important and relevant features. It is performed during pre-processing, before the learning method is executed. It performs what is known as dimensionality reduction on the data. The idea behind this technique is that removing features which are irrelevant will not lead to information loss and may even increase the classifier's performance. Other advantages: much shorter training times, lower number of computations, and improvement of the generalization capabilities of the classifier. Curse of dimensionality: more features does not necessarily result in higher performance. Using too many features can cause a variety of problems, and that's why dimensionality reduction is performed. One or more features can be redundant because they are derived by some other feature of the dataset. A way to quantify the relation between features and detect redundant ones is through correlation analysis. For categorical data, the chi-squared test. For numerical data, the covariance. The performance and the rate of convergence of a machine learning classifier depends greatly on the data being linearly separable, right? Principal component analysis is a statistical procedure that converts a set of observations into a set of linearly uncorrelated principal components. The orthogonal vectors are a representation of the original data. It is often used to visualize the data. The idea behind linear discriminant analysis is to enable instances of different classes to be far away while instances within the same class to be close. This can be accomplished by making the distance between centers of different classes large while keeping the variance within each class small. It is commonly used to perform dimensionality reduction. An example of the decision boundary of LDA. PCA versus LDA. Principal component analysis and linear discriminant analysis look for linear combinations of variables which best explain the data. LDA explicitly attempts to model the difference between the classes of data. PCA on the other hand does not take into account any difference in class. Many real-world machine learning systems are faced with data unbalance. That happens when one or more classes, labels, have significantly higher/lower instance count compared to the rest, causing an overall imbalanced distribution. Frequently, the least common values of the label are associated with events that are highly relevant for end users in tasks such as fraud detection and medical diagnosis. Example 1. Medical data where 95% of patients don't have a heart disease compared to 5% that do. A classifier that always classifies a patient on that class can have an accuracy of 95% but is obviously useless. Example 2, data where 80% of the samples are male and 20% are female. The dataset must be adjusted in order to be balanced. When faced with an imbalanced dataset, a variety of problems arise. The most obvious one is the fact that the machine learning algorithm will be trained in a biased way. When given new unseen examples to classify, the prediction will overrepresent the majority classes. Solutions: data processing approaches. Learning approaches. Data processing approaches, also known as resampling, oversampling, create new instances that belong to the minority classes. There exists a variety of methods to perform oversampling. The most common one is SMOT, where new synthetic data points are created with the help of k-nearest neighbors algorithm. Undersampling, remove instances from the majority classes until all classes share the same frequency. This approach is not employed frequently since it requires an overabundance of data. Such methods have the following advantages: can be applied to any existing learning tool. The chosen models are biased to the goals of the user, because the data distribution was previously changed to match these goals, and thus it is expected that the models are more interpretable in terms of these goals. It is worth noting that changing the data distribution may not be as easy as expected. Choosing the desired distribution of classes can be hard. A perfectly balanced distribution may not provide the best classification results. List of main algorithms: random resampling, distance-based resampling, cluster-based resampling, prototype generation undersampling, e.g. choose centroids of k-means, controlled undersampling, e.g. near-miss, data cleaning undersampling, e.g. Tomek links and condensed nearest neighbors, synthesizing new data with SMOT and its variants, AutoSyn, etc. Active learning. Modifying existing machine learning algorithms. The very popular SMOTE algorithm first oversamples the minority class by generating new synthetic data. Then it is combined with a certain percentage of random undersampling of the majority class that depends on a user-defined parameter. The SMOTE oversampling algorithm, take a sample X from the dataset and consider its k nearest neighbors, in feature space. To create a synthetic data point SNU, select one of the nearest neighbors of X and create a vector between the two data points. Multiply this vector by a random number lambda which lies between 0 and 1. Add this to the current data point to create the new synthetic data point.